Volcanic eruptions unleash the fire and fury of our planet. We fear them, but often cannot predict them. We marvel at their primal beauty, their immense destructive power, their ability to reshape landscapes and change lives forever. Volcanoes remind us that we live on a living, dynamic planet, always changing, always creating and destroying. The Earth surely had to be the only place in the solar system where volcanoes could exist, the only world so dynamic and energetic that it could breathe fire. But now we know that view is untrue. There are many places in the solar system which have volcanoes. On some of these worlds, the volcanoes do not spit fire, but ice. A moon of Jupiter rages with more than 400 active volcanoes, perpetually erupting. There are long extinct gigantic volcanoes on Mars, one as big as the British Isles. And beyond, in the dark outer depths of the solar system, volcanoes stir. It's only in the last 50 years that we have realised that Earth is not alone in its volcanism, that right across the solar system we see past and present volcanoes unleashing their incredible power. This video is about them. But to provide a benchmark, if you like, for our tour of the solar system's volcanoes, we're going to start right here on Earth, home to a huge variety of volcanic activity. Volcanic eruptions on Earth can take many different forms, each with its own unique characteristics. What are the most common forms? Plinian eruptions produce towering columns of ash and gas that can reach high into the stratosphere. A famous example of a Plinian eruption is the AD 79 eruption of Mount Vesuvius, which buried the Roman cities of Pompeii and Herculaneum under ash and volcanic debris. Another example is the catastrophic 1883 eruption of Krakatoa. Phreatic eruptions are steam-driven explosions that occur when magma suddenly and violently interacts with groundwater or surface water, creating huge amounts of steam. In 2019, 22 tourists lost their lives in a phreatic eruption on New Zealand's White Island, shown here. Effusive eruptions are gentler, with lava flows that build shield volcanoes over time. Hawaii and Iceland are examples of islands built solely by effusive volcanic eruptions. Named after the constantly erupting Italian volcano off the island of Sicily, Strombolian eruptions feature moderate explosions and lava fountains, often from small steep-sided volcanoes. Examples include Mount Etna in Sicily and Mount Erebus in Antarctica. Both regularly erupt in Strombolian eruptions. Let's move away from the Earth now to the Moon. Its surface is dominated by dark plains called mare, which consist of basalts formed 3 to 4 billion years ago through extensive volcanic activity. In addition to the mare basalts, the Apollo missions also discovered orange and green volcanic glass beads, remnants of the Moon's fiery past. However, the Moon's volcanic activity has been extinct for over 1 billion years, indicating a significant cooling and reduction in internal heat over time. These features provide important clues about the Moon's geological history and evolution, including its early period of intense volcanic and tectonic processes. Mercury's surface is dominated by ancient lava flows that cover around 40% of the planet. These smooth volcanic plains were formed by massive eruptions billions of years ago. Irregular depressions on the surface mark the sites where these volcanic eruptions occurred. Mercury's volcanic activity ceased around 3.5 billion years ago, and the planet has been geologically dormant since then. This makes Mercury a volcanic ghost, a planet with a volcanic past but no present-day activity. Venus is often referred to as Hell's Furnace due to its incredibly hostile environment, with surface temperatures reaching over 450 degrees Celsius and crushing atmospheric pressure. Mount Mons is the largest volcano on Venus, standing 8 kilometers tall. It's a massive shield volcano formed by highly fluid lava flows. Pancake domes are a unique type of volcanic feature found on Venus, created by the eruption of extremely viscous lava that spreads out into flat circular shapes. There's evidence that Venus has experienced volcanic eruptions within the past few decades, and indeed latest research says that there may be as many as 26 volcanoes on Venus active today. So what evidence do we have of current volcanic activity on Venus? Well, here are two radar images of Mat Mons taken by the Magellan orbiter in February and October 1991. In the February image, we see an almost circular volcanic vent. But by the time of the October image, the same vent has changed considerably in size and appearance, indicating an eruption has occurred. This is just one example of several similar instances where we can see changes to Venus landscape which are difficult to attribute to anything but effusive eruptions. Moving out to Mars, Olympus Mons is the largest volcano in the solar system, standing at an impressive 25 kilometers in height. That's over 3 times taller than Mount Everest. The base of Olympus Mons spans an enormous 600 kilometers, roughly the size of the entire British Isles. This colossal volcano and smaller volcanoes across Mars' Tharsis Bulge has been dormant for an estimated 100 million years. Olympus Mons is a truly staggering geological feature, showcasing the immense scale and power of volcanism on the planet Mars. Io is the solar system's most volcanically active moon, with over 400 constantly erupting volcanoes. One such eruption is shown here in time-lapse images taken by NASA's New Horizons spacecraft when it was en route to Pluto. Jupiter's immense gravity squeezes and flexes Io's interior, generating intense tidal heating that powers this volcanic activity. The volcanic eruptions on Io often spew plumes of sulfur-rich material up to 500 kilometers into space, forming umbrella-like formations as they spread out. We can classify these as a sort of Plinian eruption, although different from Plinian eruptions on Earth because of the low gravity. They are also different because of their sheer scale. Such eruptions on Earth might eject just a few cubic miles of material compared to the hundreds of cubic miles of ejecta from a typical Plinian eruption on Io. Io is constantly resurfacing itself from effusive eruptions, which we know because of the lack of craters on Io's surface. These are similar to the eruptions on Hawaii or Iceland, but on a vaster scale. The length of volcanic eruptions on Io is linked to the Moon's orbit around Jupiter. They typically last weeks or occasionally months. All of this makes Io a truly unique and fascinating world in our solar system. Europa is another of Jupiter's Galilean moons, and it has a fascinating hidden world beneath its icy surface. The ice shell on Europa is 15 to 25 kilometers thick, a frozen crust covering a vast subsurface ocean that is over 100 kilometers deep. This ocean is thought to contain more water than all of Earth's oceans put together. Europa is a prime candidate for potential extraterrestrial life. Cracks and ridges in the ice shell suggest cryovolcanism, water plumes erupting through the crust from the subsurface ocean. Jupiter's powerful gravity causes tidal flexing of Europa's ice shell, generating heat energy that may drive this geological activity. Between 2014 and 2016, the Hubble Space Telescope imaged what are believed to be plumes erupting from these cryovolcanoes, although this has yet to be confirmed. But we may be able to confirm it soon. 2 spacecraft are currently en route to Europa in order to perform extensive studies of the Moon. NASA's Europa Clipper arriving in 2030 and the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, arriving in 2031. Moving out to Saturn, Enceladus, one of Saturn's moons, is known for its dramatic geysers erupting from the South Pole. These geysers are fed by fractures or tiger stripes in the Moon's icy surface, spewing water vapour and ice particles in another example of cryovolcanism in the outer solar system. Beneath the icy shell, Enceladus has a warm interior with, it is believed, a subsurface ocean like Europa's. On the floor of this ocean, we think there are hydrothermal vents, similar to the so-called black smokers found on Earth's ocean floor, for example at the Mid-Atlantic Ridge. The plumes from the geysers have been found to contain complex organic molecules, suggesting Enceladus may have the ingredients for life. Staying with the ringed planet, we now turn to Titan. Saturn's largest moon harbours one of the solar system's most intriguing mysteries. How does Titan maintain its dense nitrogen-rich atmosphere despite billions of years of atmospheric loss? Recent discoveries point to cryovolcanism, icy volcanoes erupting volatile compounds, as the key to understanding this enigmatic world's dynamic geology and potential for harbouring life. So what is the evidence for cryovolcanism on Titan? Firstly, NASA's Cassini spacecraft observed dramatic surface transformations in western Xanadu, an area of the Moon shown here in a radar map between its 2005 to 2006 flybys, revealing new dark features consistent with cryovolcanic eruptions of water, ammonia and methane. There's also the fact that Titan's atmosphere contains argon-40, a radioactive decay product from its rocky interior, providing compelling evidence of ongoing internal geological activity, releasing gases from deep within. And cryovolcanism offers the most plausible explanation for how Titan sustains its dense nitrogen-methane atmosphere despite low gravity and continuous methane depletion over geological timescales. The existence of cryovolcanism on Titan is important for understanding this dynamic world and its habitability potential. Titan's methane cycle mirrors Earth's water cycle, with liquid hydrocarbons flowing across the surface, pooling in vast lakes and evaporating into the thick atmosphere, a phenomenon unique in the solar system. Cryovolcanic activity could sustain this cycle by releasing fresh methane from a subsurface ocean, possibly enriched with salts and ammonia, creating chemical complexity that may support prebiotic chemistry. Understanding cryovolcanism is essential for NASA's Dragonfly mission arriving at Titan in 2034, which will explore the Moon's surface and subsurface ocean for clues about prebiotic chemistry and the potential for life. Titan stands as one of the most compelling destinations in the solar system to study exotic geology, organic chemistry, and the fundamental question of whether life can emerge in environments radically different from Earth. We now move out to Neptune. Its largest moon, Triton, is known for its remarkable geological features, including active cryovolcanoes discovered by Voyager 2 in 1989. These cryovolcanoes, also referred to as geysers, erupt volatile substances such as nitrogen, methane and possibly water-ammonia mixtures. Voyager 2 revealed vast plumes rising up to 8 kilometers above the surface, driven by internal heat or seasonal solar warming beneath Triton's translucent nitrogen ice crust. These eruptions deposit dark material across the icy plains, creating streaks that trace prevailing winds and reveal ongoing surface renewal. Triton's retrograde orbit and likely origin as a captured Kuiper Belt object make this activity particularly intriguing, suggesting that tidal interactions and residual heat play an important role. Cryovolcanism on Triton provides valuable insight into how icy bodies can remain active far from the Sun, and it strengthens the case that similar processes may occur on other distant moons, with implications for subsurface chemistry and long-term habitability. And so we come at last to Pluto, surely one of the most enigmatic, puzzling and strange worlds in the whole solar system. Before the flyby of New Horizons in 2015, we had no idea what this world looked like. It was expected to be frozen and lifeless, orbiting as it does on the edge of the Kuiper Belt, that dark, cold outer zone of our solar system. Instead, we found Pluto to be a dynamic, changing world with incredibly varied landscapes and geology. Glaciers on the move, mountains of pure water ice, jumbled rocky terrains, frozen plains, plus strong evidence of past cryovolcanism. New Horizons did not see any active cryovolcanoes, but we should remember that the spacecraft was only able to observe one hemisphere of Pluto as it flew by. The other was in darkness. So we've only really seen half of this amazing world, and it's not impossible there could have been active cryovolcanoes on the night side when New Horizons flew past. Pluto's suspected cryovolcanoes include Right Mons, shown here, a 90-mile wide and 2-mile high landform. Right Mons can reasonably be described as a cryovolcanic analogue of a shield volcano on the Earth, but not a shield volcano in the terrestrial sense. Right Mons is extremely broad, gently sloping and low in profile, with a central depression reminiscent of a caldera. These traits closely parallel shield volcano morphology, which on Earth is produced by low viscosity basaltic lava spreading laterally. On Pluto, however, the lava would be water-based ice mixed with volatiles such as ammonia, erupting at cryogenic temperatures. The physics, chemistry and heat transport are fundamentally different. For this reason, scientists typically use phrases like shield-like cryovolcano rather than applying the term unqualified. Pluto is a world of mysteries. No further space missions are currently planned to return there to investigate those mysteries, so many of us will never see Pluto again in our lifetime. But New Horizons flyby emphasized something which has been a revelation during our exploration of the dark depths of the outer solar system, that worlds which logic dictated should be frozen and lifeless are not. They are dynamic, changing worlds with activity and energy. We have seen that there are volcanoes across the solar system as rich and varied as the worlds which birthed them. From the giant volcanoes on Mars to the fountains of Enceladus to the violently erupting geysers on Triton, we see volcanism right across the solar system. Some of it familiar, most of it not. But what are the engines driving all that volcanism? There are three main sources of heat which drive volcanism across the solar system. Firstly, the radioactive decay of elements like uranium, thorium and potassium has been generating heat within planets and moons for billions of years. This internal heat source is a fundamental driver of geological activity and the evolution of planetary bodies. Secondly, tidal heating from the gravitational pull of giant planets like Jupiter and Saturn can also create significant internal friction and warmth in moons and smaller bodies, as we see on worlds such as Io and Enceladus. And lastly, even after a planet forms, the residual heat left over from its initial creation continues to radiate outwards over time. These three key heat sources, radioactive decay, tidal heating and residual heat, are the engines that power the internal activity and dynamics of many worlds in our solar system. Well, we hope you've enjoyed this video about the volcanoes of the solar system. If you have, why not give it a like and leave a comment? Tell us which of the worlds we've discussed you find the most interesting. Also, support Space Oddities by subscribing to the channel and clicking the notification bell so you don't miss any of our videos. It only takes a second and is completely free. We have more than 600 videos on the channel dealing with all aspects of astronomy, astrophysics, cosmology and space exploration, which we hope you will enjoy browsing through. Thank you so much for watching. How can the moon have water? It's dry, it's dusty, it does not have weather, it has only the most tenuous of atmospheres. It's blazingly hot, it's numbingly cold. No clouds ever form above the moon, no rivers flow, no seas lap gently at lunar shores. 17th century astronomers gave the prominent dark areas on the moon the names of seas, like Mare Imbrium, the Sea of Rain. But they are not seas. They are plains of ancient lava, billions of years old. No soft spring rain will ever fall on Mare Imbrium. There's an ocean on the moon too, Oceanus Procellarum, the Sea of Storms, but no dark storm clouds will ever gather above it. So how could there ever be water on our beautiful natural satellite? One of the earliest proponents of the idea that there might be water on the moon was Harold Urey, a Nobel Prize-winning chemist who speculated in the 1950s and 1960s about the possibility of volatile compounds, including water ice, being trapped in cold regions of the moon. However, the concept became more concrete in 1961 when Kenneth Watson, Bruce Murray and Harrison Brown published a paper in the Journal of Geophysical Research suggesting that water molecules from cometary impacts or outgassing could migrate to and become trapped in permanently shadowed regions at the lunar poles. Between 1969 and 1972, the Apollo astronauts returned nearly 600 pounds of rock and soil from the moon. The samples underwent intense scrutiny from scientists around the world, a study which, nearly 60 years later, still progresses today. But no water was found in the lunar samples, confirming what scientists thought they knew, that the moon is completely dry. But then in 1976, the Soviet Luna 24 mission brought back soil samples with traces of hydroxyl, but this was largely overlooked. Hydroxyl, or OH to give it its chemical formula, is a molecule consisting of one oxygen atom and one hydrogen atom. It is not the same as water, but it is closely related. Hydroxyl can form when water molecules break apart or interact with minerals. In the context of the moon, it likely forms through interactions between the solar wind and oxygen in lunar minerals. It's a key indicator of water-related chemistry on the moon, even if it is not in liquid form. In 1994, NASA's Clementine mission detected reflections at the lunar poles, suggesting the possibility of ice deposits. Then, in 1998, NASA's Lunar Prospector found hydrogen signatures near the poles, interpreted as potential water ice. However, the images returned from both spacecraft were of such low resolution that the discovery of water could not be confirmed. This picture is a later image of the moon's south pole by NASA's Lunar Reconnaissance Orbiter, the water marked in blue. But then, in 2008, reanalysis of Apollo samples by Brown University scientists found both hydroxyl and water molecules. It seemed that initial analysis of the Apollo moon rocks had overlooked them due to the inadequate analytic technology of the time. Then, in 2009, India launched their Chandrayaan-1 spacecraft to the moon. Mapping the moon's surface with an X-ray spectrometer, the spacecraft created maps of mineral deposits. But it also released a small impactor, which, striking the moon's surface, also detected both hydroxyl and water molecules. NASA's LCROSS mission, launched in 2009, aimed to confirm the presence of water ice in permanently shadowed lunar craters. The mission targeted the Cabeus crater near the moon's south pole, where previous data suggested potential ice deposits. LCROSS deliberately crashed its Centaur rocket stage into the crater at high speed, creating a debris plume. The LCROSS spacecraft, following closely behind, analysed the ejector before it too impacted the surface. The debris plume was also analysed by NASA's Lunar Reconnaissance Orbiter, or LRO. Instruments detected water ice along with other volatiles, confirming that significant amounts of frozen water exist in these shadowed regions. This discovery was a major milestone, strengthening the case for future lunar exploration and resource utilization, including human missions and potential in situ resource use. LCROSS provided concrete evidence that the moon holds accessible water, which could be critical for sustaining long-term lunar bases. There may be more than 1 billion tons of water ice locked up in the permanently dark craters at the moon's poles, where the temperature is a constant minus 230 degrees Celsius. So where did it all come from? Water-rich comets and asteroids bombarded the moon in its early history, particularly in a period about 3.5 billion years ago known as the Late Heavy Bombardment, depositing ice that became trapped in permanently shadowed craters. It may also have come from hydrogen in the sun's solar wind reacting with oxygen in lunar minerals to form hydroxyl and small amounts of water. There were also ancient lunar volcanic eruptions which released water vapour, some of which could have migrated to the poles and become trapped in cold regions. And the moon is constantly being bombarded with small meteoroids containing hydrated minerals, delivering water molecules to the moon over time. That water ice can be used by future human bases on the moon. It could be used to extract the oxygen from the ice for breathing, further processed to produce rocket fuel, be used for radiation shielding, agriculture, hydroponics, thermal regulation, industry and many other applications. All we need to do is to find the ice and figure out an extraction and transportation system, but there is no doubt that the ice is there in large amounts. In 2023, India's Chandrayaan-3 spacecraft landed at the south pole of the moon to search for water, but only detected hydrogen and oxygen separately, not as H2O. The US and Russia have also launched spacecraft to find the water, but so far their missions have failed. However, the US, Russia, China, India and Japan are all sending missions to the lunar south pole to search for the water over the next couple of years, so it's likely that at least one of those countries will find the water and eventually construct a base at the south pole of the moon. It's taken 70 years since the first suggestions that there might be water on the moon, but at last it looks as though we may find it and use it for the advancement of human lunar exploration. And there you have the story of water on the moon. Thank you for watching, and I hope you'll watch the other videos in the Space Oddities Moon Month series. Check out the Moon Month playlist on the Space Oddities channel. Sometime in the not too distant future, a spacecraft will leave Earth orbit and head out across the solar system. Its destination, Mars, the only planet in the solar system where we stand a chance of establishing a foothold, where we might be able to live even in an extremely dangerous environment. And for more than 100 years we've dreamed of walking on its surface. Mars is reminiscent of deserts on Earth. It's completely dry, no water has flowed across its surface, nor formed lakes or seas for billions of years. It has huge canyons, rolling sand dunes, ancient river valleys. But while it might look familiar, Mars poses a level of danger to humans unlike anything we've ever experienced on Earth. There are many ways of dying on Mars. Future explorers will live on a knife edge where one tiny mistake can have fatal consequences, where just staying alive will be a constant struggle. So what dangers will future Mars explorers face, and why is Mars such a dangerous planet? Assuming that astronauts have survived the physical and psychological challenges of a 6-month journey to Mars, far longer than any crewed space mission beyond Earth orbit ever attempted, the most dangerous hazard they will face is radiation, charged particles from the Sun and the wider galaxy. Mars has no global magnetic field to shield astronauts from solar and galactic radiation as we have on the Earth. It's estimated that a 3-year round trip to Mars will give astronauts, if they're not adequately protected, radiation doses above the safe limit for their entire lifetime. To put it another way, each unprotected astronaut on Mars would receive the equivalent of 7 chest X-rays during one Martian day. Prolonged exposure to solar and galactic radiation can lead to nausea, sickness and ultimately death. so spacesuits would have to be lined with materials which can block at least some of the radiation. NASA are experimenting with a material called Demron, which can do just this. It could be incorporated into both spacesuits and the structure of a Martian base, as well as garments astronauts might wear inside the base. As yet, however, there's no data as to how effective Demron is against harmful levels of radiation, but it is thought to be promising. Even so, astronauts will probably need to be outside for limited periods, as any protection in their suits will not block all the harmful radiation. Their base will need extremely high levels of protection. But is there an alternative to the domes of a future Mars base being constantly exposed to the potentially lethal charged particles raining down from the Martian sky? This is the entrance or skylight of a collapsed lava tube on Mars, as imaged by NASA's Mars Reconnaissance Orbiter, or MRO. It dates from Mars' volcanic past, billions of years ago, before the core of Mars froze and all volcanic activity ceased. Radar surveys indicate these lava tubes, several dozen have so far been identified, are at least several tens of meters deep and extend underground in tubes which may be hundreds of meters wide. The skylights themselves are also several tens of meters across. These lava tubes would be an ideal place for a future Mars base, shielded from the solar and galactic radiation by tens of meters of solid rock. However, this would not be the first base on Mars, but rather a long-term solution. Before a base could be built underground, extensive surveys by ground-penetrating radar and robotic vehicles would be required before any astronauts could descend into the depths, and this could only happen after an initial base were established on the surface. A crewed mission to Mars will embark upon a journey which will last for a minimum of 2.5 years. This is not by choice, but because Earth and Mars align only every 2 years, so that the journey to the red planet can be cut down to 6 months. At this point, when the two planets are at closest approach, they are between 50 and 60 million kilometers apart. The mission profile would therefore be a 6-month journey to the red planet, then 18 months spent on the Martian surface to await the next alignment of the planets, followed by a return to Earth lasting another 6 months, a total time of 2.5 years. This is the shortest possible duration for a mission to Mars with current technology. But what effects will such a long journey, such prolonged isolation, have on the human mind? Since the beginning of manned spaceflight, scientists have studied the effects of long-duration space missions on the human mind, but these experiments only started in earnest after the construction of the International Space Station, which has become an orbiting laboratory for studying the physiological and psychological effects of prolonged space missions on the body and mind. In general, the studies have shown that astronauts can experience a range of psychological challenges during long missions. These can include feelings of isolation, disrupted sleep patterns, and sometimes even mood changes. However, the studies have also shown that with the right support systems like communication with family, structured schedules, and engaging tasks, astronauts adapt quite well. However, the longest that anybody has spent on the ISS is 371 days, a record held by astronaut Frank Rubio. This is obviously far short of the 2.5-year duration of a mission to Mars. But there has been an attempt to understand the psychological effects of longer duration space missions. It was called the Mars 500 experiment. The Mars 500 experiment, carried out between 2010 and 2011, was a ground-based simulation designed to replicate a full-length mission to Mars. It involves 6 crew members living and working in an isolated, confined environment for 520 days. The experiment used 5 interconnected modules with a total volume of about 550 cubic meters. The main habitat module itself was roughly 3.6 meters in diameter and 20 meters long, providing living quarters for the 6 crew members. The facility also included a medical area, a storage module, and even a simulated Martian surface module. The objectives were to study the psychological and physiological effects of long-duration space flights. The results showed that while the crew experienced some challenges like monotony and sleep disruption, overall they adapted well, providing valuable insights for future Mars missions. But as the first Mars astronauts watched the Earth slowly receding, as everything they have ever known shrinks behind them, as they begin to sense the infinite vastness of space, how will they feel knowing they will not return for years? As the gaps in the radio chatter get longer and longer until it becomes impossible to have a conversation with their loved ones, will the weight of their total isolation bear down hard on them? They will have been selected for both their physical and psychological resilience, but no human beings will ever have been more alone, so cut off from their lives on the Earth. There will be no door of a prison cell that can be thrust open to let the daylight stream in, no blindfold that can be removed to escape the darkness. When the Earth becomes just a distant blue dot among the stars, nobody really knows what that will do to the human mind. Can any amount of training truly prepare them for this? During the days and weeks following the Mars landing, the astronauts will be kept constantly occupied, requiring immense amounts of coordination and teamwork to build a habitat. They will probably push their possible feelings of isolation to the back of their minds during this intensely busy period. The astronauts will need to acclimatise to working in gravity that is only 38% of the Earth's, learning how to move around deliberately and safely. One fall on a jagged rock could be fatal if it were to rip open their spacesuit. So how far they are from the Earth, how isolated, and how they will face the long haul ahead, the 18 months before they can return home, will doubtless not be prominent in their minds. But when they are alone during those long months with time to reflect, how might feelings of loneliness and isolation prey on their minds? Only the very toughest of minds will be able to deal with these emotions. Psychological support for the astronauts, therefore, is going to be a crucial part of the mission. At the end of the day, however, we will be very much in uncharted territory. This is British astronaut Tim Peake doing an experiment on the International Space Station to see if he can make himself dizzy. The answer is, somewhat surprisingly, that he could not. When astronauts first arrive on the ISS, they often do feel dizzy and nauseous because their vestibular system, the liquid in the inner ear which, acting like a gyroscope, tells your brain which way is up and therefore allows you to balance, is contradicting what the astronaut is actually seeing. However, after a couple of days of eyes and ears contradicting each other, the brain shuts the vestibular system down and relies instead on visual cues to establish orientation. This is why Tim Peake didn't get dizzy. While the dizziness and nausea are perhaps a temporary inconvenience for astronauts, these effects of being in a microgravity environment are minor compared with more lasting and damaging physiological effects that can be suffered during a long-duration space mission. Floating in space might look fun, but it's potentially extremely harmful to humans. There are many physiological effects caused by prolonged periods in microgravity. Most severe are muscle loss and bone weakness. To combat these, astronauts on the International Space Station must perform long periods of exercise every day. When they return to Earth, they are often unable to stand, and they experience several days of readjustment to normal gravity. One way of combating the adverse physiological effects of microgravity is to rotate the spaceship or space station, as depicted here in the classic film 2001: A Space Odyssey, in order to provide artificial gravity. How much gravity could such a rotating structure generate? It depends on two factors: the rate of rotation and the diameter of the structure. As for the rotation rate, 2 rotations per minute would be a comfortable speed so as not to disorientate the crew. Such a structure attached to a spaceship bound for Mars would need to be 448 meters in diameter to provide 1 g of gravity, in other words the same gravity as on the Earth. That would be a huge construction. On the other hand, if you wanted to generate just a third of Earth's gravity, the diameter required for the rotating structure would shrink to just 75 meters. A third of Earth's gravity would greatly lessen the adverse physiological effects on the astronauts. Coincidentally, a rotating structure of around the 75-meter diameter size was portrayed in the marvelous sequel to 2001, 2010, the year we make contact. It provided artificial gravity on a Russian spaceship headed for Jupiter. Generating a third of Earth's gravity would mean that the astronauts, instead of having to exercise for 2.5 hours daily as a minimum to remain healthy, as they currently have to do on the ISS, might have to exercise for just an hour or even less. A third of a G of gravity would be sufficient to keep their circulatory systems functioning correctly and stop the pooling of fluids in their bodies, which is a major danger in microgravity. And a third of Earth's gravity is about what they will encounter on Mars, so it would help to acclimatise them and teach them how to move about safely in the Martian environment. When the astronauts reach Mars, they will have to do daily exercise to prevent muscle and bone loss, circulatory problems, and other adverse effects on the human body. How much exercise they will need to do is unclear, although there is a lot of research being conducted into how to keep them healthy on Mars. Perhaps a centrifuge or even a slowly rotating habitat might be a solution. However, studies indicate that working in just 38% of Earth's gravity could lead to bone density loss of 1 to 2% per month if not countered. Reduced blood volume and cardiac atrophy may impair explorers' ability to function effectively in Martian gravity. In addition, loss of muscle mass during the 6-month voyage and continued loss on Mars could compromise mission operations and emergency responses. As far as actually working in just a third of Earth's gravity goes, that is somewhat less of a problem. The Apollo astronauts very quickly learned how to work and move about in a 1/6 of 1G on the Moon, although they did sometimes slip and fall, luckily safely. And as we said earlier, on the journey to Mars, if the astronauts can become acclimatized to Mars gravity in a rotating structure generating a third of Earth's gravity, that will greatly help them during their stay on Mars. Working outside on Mars presents a number of challenges: the low gravity, the extremes of temperature, the constant danger of falling onto sharp rocks. But there is another, more insidious danger: dust. Martian soil contains perchlorates, a highly oxidized compound of chlorine. Perchlorates are extremely toxic to humans. If ingested, they can attack the thyroid gland, leading to sickness and weight gain in addition to other health issues. Although the amount of perchlorates in Martian soil is small, perhaps 0.7% by weight, they nevertheless pose a real health risk for Martian explorers. In addition, the soil is made up of extremely fine, extremely sharp particles with the consistency of something like talcum powder, posing another danger. These particles are also electrostatically charged, meaning they will stick to everything, including astronaut spacesuits. Every 7 to 8 years, Mars experiences dust storms, which blanket the whole planet for weeks. Obviously, missions to Mars will be timed to avoid these global dust storms, but there is another danger whereby Martian soil can be stirred up and blown across the surface: Martian dust devils, as imaged here by NASA's Spirit rover. Even though Mars' atmosphere is only 1% of the thickness of the Earth's, it's still dense enough for these dust devils, stirred up by summer heat, to blow across the surface, elevating dust into the atmosphere as they go. Martian dust stirred up by any sort of activity on the surface can settle on solar panels, causing their efficiency to drop. It can penetrate into seals, into spacesuit joints, electronic equipment everywhere. There will need to be thorough decontamination procedures for astronauts entering the base from outside and the regular cleaning of equipment on the surface. But there's another danger from the dust: electricity. It's been calculated that rapidly rotating Martian dust devils can generate up to 4,000 volts of static electricity. This would be enough to knock out the radio of any astronaut unlucky enough to be outside when a dust devil passes over them, leaving them in an extremely dangerous and isolated situation. Martian dust, as we have seen, will be an ever-present danger for astronauts and equipment on the surface of Mars. It will be crucial to prevent critical systems for power generation, life support, water recycling and food production from suffering contamination and degradation from the dust, as well as preventing astronauts from suffering damage to their health. A rigid decontamination and maintenance regime will be of the utmost importance. Mars is an inhospitable, extreme environment, exceptionally dangerous to humans. All of the challenges we have looked at in this video can doubtless be overcome in time, but the time is not quite yet. Establishing a base on Mars is still some way off. We are just not ready, the technology unproven, and the possible effects of such a long space mission on humans not well understood. But we humans are endlessly resourceful and ingenious, so it's almost certain that one day our dream of walking on Mars will be realised. Well, we hope you have enjoyed this video. Check out the other Space Oddities Mars Month videos. You'll find a playlist called Mars Month on the channel, which we will be adding to during September 2025. Please also subscribe to the channel and watch our Tuesday live streams during September, where you can join in our discussions about Mars. You might also consider joining our Patreon community, which you will find at patreon.com/Space Oddities. Thank you so much, and we'll look forward to seeing you.